all, welcome to the lecture series on Aerospace Propulsion. Today, the topic which we are going to discuss is escape velocity. Myself, Mr. Manideep Gupta, Assistant Professor, Department of Aeronautical Engineering from MLR Institute of Technology. So, coming to the overview of today's presentation. So, today we are going to discuss about what is escape velocity, and we calculate the escape velocity from Earth to surface and escape velocity from an orbit, and some problems on the discussed topics earlier. So, coming to the first, what is escape velocity? So, escape velocity is nothing but velocity provided to a body. Okay, velocity provided for a body to overcome the gravitational attraction to an infinite radius. Okay, from which it will escapes from the gravitational field of the parent planet or parent object. So, whatever the velocity provided, if you provide any velocity so that it will overcome the gravitational attraction to an infinite radius to escape from the attractive force of the planet, is called escape velocity. Right. So, what to calculate this escape velocity? So, here we have to send an object from the Earth. Suppose if you take the Earth, now for example, if you consider the Earth, okay, so we have to send an object from Earth surface to an infinite radius. So, to do that, we have to do some work, right? To do that, we have to do some work. So, we should calculate the work done by the object to move from Earth surface to the infinite radius. So, work required to move the body from surface of the planet to infinity should be calculated. So, whatever the work required, that much amount of kinetic energy to be provided for the body, this energy should be provided for the body so that it will move to the infinite radius. So, let us calculate this escape velocity. So, if I take the kinetic energy required for a body, then for a of mass m, okay, consider mass m, and if I consider Ve is the escape velocity is Ve, then the kinetic energy provided by the object is half mve square, and this is equal to the work required to move from the Earth surface. So, work required is nothing but the force into displacement. Yes. So, what is the force acting here? The gravitational attraction force, that is capital G m by r square into distance. Distance is nothing but the radius or the infinite radius or infinity. So, as this force is varying depend upon the radius, so I will take dr here, and I will integrate this force from Earth surface, that means the radius of the Earth, to the infinity. Okay, then I will get the energy, kinetic energy required or kinetic energy to be provided for the object so that it will escape from the parent object gravitational force. Okay. So, if I take this, if I integrate this Re to infinity, from Re to infinity, then it will become 2 capital G me into into integration from Re to infinity 1 by r square dr, and this will be 2 G me by Re. So, Ve square, okay, and here get cancelled and 2 will come to the right side, then Ve square is equal to capital 2, okay, Ve square is equal to 2 G me by Re, and if I send, okay, if I send this square, on the right side, then it will become under root. So, then the equation for Ve is under root 2 into capital G me by Re. Okay, Ve is equal to under root 2 into capital G me by Re. So, what is capital G? You know already, right? Capital D is a gravitational constant, me is the mass of Earth. So, here we want to send the object from the surface of the Earth. So, the mass of the Earth should be considered here. So, the mass of Earth is me, and radius of Earth. So, why radius of Earth? So, we are sending the object from the surface of the body. We are sending the object to the infinity from radius of the Earth, from the surface of the Earth. So, that is why Re here. So, finally, if you see the equation, it is under root 2 into capital G into me by RE. And even in the previous discussion, we have gone to the equation of orbital velocity, that is equal to under root capital G me by RE. So this is the equation for orbital velocity which we have derived in the earlier classes. Okay, so if I substitute this V0 is equal to under root capital G mu by RE, then this equation will be V is equal to under root 2 into V0, root 2 into V0. So from this we can conclude that escape velocity VE is equal to root 2 times the orbital velocity. Escape velocity of any object, okay, escape velocity is equal to root 2 times the orbital velocity, right? And here you can see the graph how the escape velocity is varying with respect to the altitude. If you go to the escape velocity, and here you can see the escape velocity is decreasing. Escape velocity is decreasing as the height of the object from the radius of the object increases. So if I want to escape an object at a radius from at a distance of 10 kilometers, okay, 10 kilometers. So this is the escape velocity I needed. Suppose I want to escape an object which is rotating or which is at a height of 100 kilometers from the earth, okay, 100 kilometers altitude, then this is the escape velocity. Okay, suppose, and this is 0 kilometer altitude, 0 kilometer. Suppose if I want to send the object to escape from its earth gravitational field, then this is the velocity required to escape from the earth surface. So that we have already calculated, that is 11.17 kilometers per second. Speed is required for an object to escape from the earth surface. Okay, as the altitude increases, the escape velocity decreases. Here at 10,000, you can observe this is the escape velocity required for the object. So if the same way, if I consider the height of 50,000 kilometer, then the escape velocity required is around 3.76 kilometers per second. Right. So the escape velocity which we have, if you go through the equation once, V is equal to under root 2 into capital G me by RE. Okay, so this is the equation which is for an object which has to escape from earth surface. Suppose I want to send an object which is rotating in a particular orbit. Okay, this is an orbit and the radius is r. Okay, I want to escape an object which is escape a satellite which is rotating in a particular orbit of radius r to the infinity. So what will be the equation? Simply you have to change this RE with the radius of the orbit. Then you will get the velocity, equation of velocity for an object which is rotating in a orbit of radius r. Okay, simply then the equation will become VE is equal to under root 2 capital G me by r. Okay, so this is the equation for to escape velocity. It is the equation for escape velocity from the earth or from an object which is at a orbit radius r. Suppose I want to escape an object from the moon's gravitational field, then simply I will replace this mass of the moon with mass of the earth with mass of the moon. That's it. Then this equation will become VE is equal to under root 2 into capital G into mass of the moon divided by radius of the moon. Okay, so if you carefully observe here, the equation which we have, VE is equal to under root 2 capital G m by r. So m is the mass of the parent body. M is the mass of the parent body. M is the mass of parent body. Okay, and r is the distance of object from the center of parent body. Okay, r is the radius from the center of an object. So this is actually the basic equation to calculate the escape velocity from any object or from any planet. V is equal to under root 2 into capital G into mass of the parent planet divided by radius of the object or the distance from the center. Okay, so this is about the topic escape velocity. So next we'll discuss some problems. Okay, next we discuss some problems regarding from the topics which we have already discussed. Okay, so if you see very simple, I will start with very simple problems. Okay, if a force of 10 newtons, acting on a body of mass 2 kg, find the acceleration of the body. Okay, here the force is given, F is equal to 10 Newton and mass M is equal to 2 kg and is asking acceleration. So we know the basic equation that F is equal to ma. So if I apply F is equal to 10, mass is equal to 2 and acceleration is a, then I will get a is equal to 5 meter per second square. So what is the answer here? So answer is 5 in units are meter per second square. If the equation is simply F is equal to m into a, basic equation. So next, second problem. So here he is telling a body of mass, okay, a body of mass 100 kg while traveling along a straight line increases its velocity from 5 meters per second to 45 meters per second. Calculate the change in momentum of the object. Okay, so first let's note down the given data. So mass of the object is 100 kg. Okay, m is equal to 100 kg. So it is traveling along a straight line. It is traveling along a straight line like this. Okay, line increases its velocity from 5 meters per second to 45 meters per second. So if I consider this is the first point and this is second point, here the velocity v1 is equal to 5 meters per second. Okay, and at it increases to 45 meters per second. So v2 is equal to 45 meters per second. So calculate the change in momentum of the object. So what is momentum? What is momentum? Momentum is mass into velocity. So change in momentum is delta mv. So delta mv is equal to final momentum m2v2 minus initial momentum m1 v1. So is there any change in mass of the body? So mass of the body is fixed, that is 100 kg. Mass of the body is 100 kg. Then we have to imply, if I can take 100 common here. So v2 is 45 minus v1 is how much? v1 is how much? 5. Okay, 100 into 45 minus 5, that is 100 into 40. So I will get how much? 4000. So what are the units for momentum? Change in momentum. Mass kg, velocity is meter per second. So kg meter per second. Okay, let us see the answer. So yes, so answer is 4000 kg meter per second, which is option A. Okay, so this is, he is asking momentum, change in momentum. So first you should know what is momentum. Okay, that is mv. After that he is asking change in momentum, that is delta mv. If you substitute all this, then you will get the answer, that is 4000 kg meter per second. So here the velocity of an object, okay, he is giving the velocity of an object with a mass of 5 kg. So object mass is 5 kg given, changes with respect to time. So the velocity is changing with respect to time. So here we can assume either the body is accelerating or it can be decelerating. So but he is given according to the figure. So the velocity is changing with respect to time according to the figures 1 and 2. So this is figure 1 and this is figure 2. Okay, what is asking? Let us see what is asking. Find for the cases in the figure 1 and 2, what do we have to find? Impulse imparted between time 1 to time 2 seconds. So he is asking to calculate impulse. He is asking to calculate impulse from which point to which point? Time 1 second to time 2 seconds. So this is the time 1 second and this is time 2 seconds for both cases. Okay, so what is impulse actually? What is impulse? Impulse is nothing but change in momentum, delta mv. We have already gone, we have done in the previous. So m2 v2 minus m1 v1. So if you do for case 1, so mass is same, so m into, we can say v2 minus v1, right? So case 1 between time 1 to second. So this is 1 and this is first second and this is second. So now we have to calculate, we should note down the velocities at time 1. So if I go to the velocity, so this is the velocity at time 1. So v1 is equal to 2 meters per second, and at second, this is the second velocity. So I have found that v2 is equal to 3 meters per second. So if I substitute, mass is equal to how much? Mass is given as 5 kg. So 5 into 3 minus 2. So I will get 5. I will get answer is 5 in the first case. So the answer is 5 here. Okay. Similarly, we will find for the second case. So the second case also is asking the impulse between first second and second. So if I go and find the mass is same, right? Mass is same. M into v2 minus v1 for the second case also. Okay. So mass is 5 kg and we have to find v2. So at a second, what is the velocity? 2. And even at the first second, the velocity is 2 only. So 2 minus 2. So finally what? 5 into 0, that is 0. So impulse at second case is 0 and impulse at first case is 5. So we can easily observe that in the figure. So impulse, low impulse here, at second the impulse is increased. But here, if you observe this graph, velocity is increased and decreased. But impulse only explains the property before and after. Okay, between, not it doesn't consider what happens in between the time. Okay, it will just consider the property at the initial and final. So if you consider the initial momentum is same and the final momentum at second is also same. So whatever it may happen, even the velocity increases, decreases, it doesn't bother about that. So that's why even we need force to explain the actual motion of your body, right? So impulse in the second case is 0 and impulse in the first case is 5. Here it is 0, right? Next problem. Here he is giving the same, I think the graphs are same. The mass of the body is also 5 kg. What is asking? Average force applied on the object between time 1 and 2 seconds. He is asking the average force applied on the body. So you know the average force delta F is equal to impulse per time. Impulse per time. So we have already calculated impulse for this is 5 and for impulse for this second case is 0. So if I calculate the average force delta F for the first case, impulse by time. So what is impulse? 5. What is the time? 2 to 1. So 2 minus 1, 1. So delta F is equal to 1 Newton. Sorry, 5 Newtons. For this case, delta F is equal to I by time. So impulse is equal to 0 and time is equal to 1. So average force applied on the body is also 0. Okay. So here if you see here, this is a positive force and here this is a negative force. So both are same. So average force, positive plus negative, you can get it is 0. So average force applied in the second case you got 0 and here it is 5 Newtons in the first case. Okay. Next. Okay. If you go to the fifth problem, consider an asteroid. Okay. Consider an asteroid of mass 1000 kg. Okay. Consider an asteroid of mass 1000 kg drifting in a space. So just an asteroid, it is moving randomly in the space. If it is passes by the earth with the closest approach a distance of 1 lakh kilometers. So consider, I am considering earth here somewhere else and the distance is what is given 1 lakh. The distance between the centers. Okay. Centers of these two planets is 1 lakh kilometer from the center of the earth. So find the acceleration felt by the asteroid at the instance because of Earth's gravity. So he is asking the acceleration acceleration due to gravity acting on the asteroid by the Earth. So we know the equation, right? F is equal to capital G m1 m2 by r square. So this is the force acting on the body. So this force acting on the body is nothing but the weight, that is right, m1 into, so if I consider this this is Earth and okay, this is asteroid, mass of the Earth into mass of the asteroid. So mass of asteroid into gravitational force acting on the asteroid, ma into g. So ma get cancelled. So finally what is capital G? Small g is equal to capital G into mass of the Earth by r square. So we know so we have to substitute capital G. So capital G is given 6.674 into 10 to the power of minus 11. Okay, substitute capital G here, and mass of the Earth is 5,974. Okay, into 5.974 into 10 to the power of 24 kgs. So if you apply this and r is equal to 1 lakh kilometer, then you will get the answer. Okay, capital G into me by r square is nothing but the acceleration due to gravity acting on the asteroid at a distance of 1 lakh kilometer from the Earth center. So if you see the answer, this will be 0.0399. You can do this calculation in Calc and you can cross check the answer. Okay, next another problem. Calculate the acceleration due to gravity of moon on any object that is on the surface of the moon. The same formula. Now he is asking to calculate the acceleration due to gravity on the moon surface. So now I will consider the moon. Okay, so what is the formula for acceleration due to gravity? Capital G into mass of the parent planet. So what is the parent planet here? Moon. Capital G m by r square. So radius of the Earth, radius of the, we have to consider the radius of radius of moon. Why we have to take radius of moon? Because he is asking the acceleration due to gravity on the surface of the moon. Okay, on the surface of the moon, and capital G is same, that is 6.67 into 10 to the power of minus 11, and we should know the mass of the moon. So mass of the moon is given here 7.347 into 10 to the power of 22 kg, and radius of the moon, you have to apply you have to substitute radius of the moon, then you will get the answer as 1.636 meters per second square. 1.636 meters per second square is the acceleration due to gravity on the moon's surface due to the moon's gravitational force. Okay, so next another problem. Calculate the orbital velocity v0 in meter per second. So he is asking to calculate the orbital velocity v0. Okay, for what? Required for placing a satellite of mass 1000 kg at an altitude of 150 km and 1500 km above the Earth's surface for an altitude of 1. Okay, right? He is asking to calculate the orbital velocity to place in 150 km altitude. Okay, so what is the formula for orbital velocity? V0 is equal to under root capital G me by r. So mass of the Earth, substitute mass of the Earth, capital G, and r, here radius of the object is, this r is equal to radius of the Earth plus height. What is height? Height is 150. So radius of the Earth plus 150 for the first case. Then you will get the velocity, orbital velocity for 150 km altitude orbit. And if you substitute Re plus 1500 km for the second, then you will R is equal to Re, then you will get the orbital velocity for the second case. Okay, so for the first case and second case, these are the 78127816. Okay, so this is the orbital velocity required to place an object. Okay, right, and in the next, if you want to next problem 8, calculate the same case. Okay, consider the same case. The mass of the satellite is 2000 kg. So what is the formula for V0? Under root capital G into me by r. So is there any mass of the body given? In the equation you don't have any mass of the body. So whatever the mass, whether the mass of the body is 1000 kg, 2000 kg or 1 lakh kg, that is not a matter. But orbital velocity does not change. Orbital velocity is independent of mass of body. So answers for this case and this case both are same. So this is about some basic problems on the topics which we have discussed till far. Okay. So coming to the summary. So today we have gone through the escape velocity. What is escape velocity? And we have calculated the escape velocity from Earth surface to an infinity. And we have calculated we have generated an equation for escape velocity from an orbit. And we have discussed some problems. Right. So this is about the summary of today's lecture. Thank you.